So the next one is adiabatic process. So that we have discussed the adiabatic process, for example, the bursting of tire. Yeah, so it's a very fast rapid process. So definitely you can say for that case, so that is nothing but what we can say about the adiabatic process. You have to compress that gas, yeah, or you have to just make sure that you are going to expand the gas suddenly. So the process is very fast and there is no exchange of heat, so you are not going to provide any heat to that your gas. So means you are not expecting, you are not providing any input, but still you are expecting that the gas should do some work. Yeah, so that means that is how we can say about this your adiabatic process. Yeah, so which occurs transferring heat or mass between a thermodynamic system and its surrounding. So again, so that is what we can call it as the adiabatic process. So this is nothing but the non-conducting walls. So there should not be any exchange of heat with the surrounding. So you have to make the wall should be non-conducting or insulating, and this is again a very quick process. So which is nothing but we called it as nothing but adiabatic process. If it's a slow process, then it is a isothermal process. But since this is a very quick process, we call it is nothing but adiabatic process over here. So now you have to find the relation between P and V for this particular case over here. So what we can do, again this dq is equals to du plus P into dV. Now since dq is equals to 0, there is no exchange of heat with the surrounding. So again we can write it down for that du. Yeah, so what you can write it down for that du, which is nothing but your Cv into dt. Yeah, so if you see that what we have written, that q is equals to u plus P dV at constant volume. Yeah, so this dq upon dt, and which is nothing but du upon, again this is what we can say over here. So this is dt and this is at constant volume, this has to be 0. This is nothing but Cv dt is equals to du. Fine, so this one I can write it down. So this is 0 is equals to Cv dt plus P dV is equals to 0. Yeah, so this is how we can just write it down, this equation over here. Again further I can write it down, this PV is equals to RT, P is equals to RT upon V over here. So this is 0 is equals to again Cv dt, again this RT upon V. Yeah, and again this is dV. Yeah, so again instead of this we can do one more thing. You can just take the differentiation on both the sides. First we can just take the differentiation on both the sides, and then you can put the values for over here. So if I just write it down, that PV is equals to RT, so this is P dV plus V, dP is equals to R into dt. Yeah, so P dV plus V dP upon your R, so which is nothing but your dt. Fine, so this is how you have to just put down the values over here for this case, which is Cv dt. Yeah, so let's say this is Cv dt P dV is equals to 0. Yeah, and we have just written dt is equals to P dV plus V dP. Yeah, so P dV plus V dP, again that is nothing but divided by R. So this is your dt plus P dV is equals to 0. Now just simplify it. So Cv P dV plus Cv V dP plus PR dV is equals to 0. Then take that dV common, so then you will get, so P dV. Yeah, so you have to just take P dV common, this is P dV, so this is P dV. So you can say that this is Cv plus R, then this is P dV plus Cv V dP is equals to 0. Cp minus Cv is equals to R. So you can say again this Cp is equals to Cv plus R. So Cpp dV plus again Cvv dP. Yeah, again just divided by Cpv. Yeah, so definitely finally you will get that PV raised to gamma is equals to K, and that gamma we know that it is your Cp upon Cv. So this a ratio of specific heat, gamma is equals to Cp upon Cv. So this is the equation for your adiabatic process, PV raised to gamma, which is equals to K, which is very important. Now we will find the adiabatic relation between P and T, that is a pressure and temperature. So what we know, basically the equation we are having, that is a PV raised to gamma is equals to K. Now we want that P and T, so we don't want V over here. So this is PV is equals to RT, so V is equals to RT upon P. So just keep this P as it is, then this is RT upon P, yeah, raised to gamma is equals to K. So what we can say for this particular case over here, so this is P, okay, again we can say that, so this is 1 minus gamma, yeah, and again this is T raised to gamma, and this is some constant K. So this is how we can just find the relation between that. So P, that is a 1, yeah, again this is what we can say that, so this is 1 minus gamma T raised to gamma is equals to K. So that is the relation between P and T over here. So when you are to find the adiabatic relation between P and T, so you have to just eliminate that V over here and then just simplify, you will get this is the final relation between them. Similarly, you can find the adiabatic relation between V and T also. So PV raised to gamma is equals to K. We know that again PV is equals to RT. So again it is a V and T, so you don't want P actually, so RT upon V, yeah, so this is RT upon V and this is V raised to gamma is equals to K, yeah, so then this is T and again this is gamma minus 1 is equals to K. So this is the relation between your temperature and your volume, and that gamma is obviously that is a ratio of specific heat. So this is how you can get the relation between V and T. Either you can get the relation between P and T also, or even you can get the relation between the previous one was your PV raised to gamma is equals to K over here. Now we have to find what is the work done in an adiabatic process. So the work done formula we know, obviously it is a PdV, it is from V1 to V2. So what we know that PV raised to gamma is equals to K. So from this P is equals to K into V raised to minus gamma, yeah. So you can just put down those values V1 to V2. Again this one you can write it down that K V raised to minus gamma into dV over here, yeah. So you have to just take, obviously K is constant, that is V1 to V2. Again you can just V to the power minus gamma dV, fine. So this is V to the power minus gamma plus 1, yeah. So this is how we can just do these things. So just write it down that minus gamma plus 1 for this particular case, again that is a 1 minus gamma, again it is from V1 to V2. So this is your work done. Again I can further simplify for this. So this is your K upon 1 minus gamma is constant. Further again you can write it down, that is nothing but V2 1 minus gamma and again minus V1 1 minus gamma over here. So this is about the work done. So further I can just make few changes over here. So I can write it down that as a gamma minus 1. So K upon gamma minus 1, which is your work done. Then this one will become V1, again that is a V1 raised to 1 minus gamma minus V2 raised to 1 minus gamma over here. So further what we know that PV raised to gamma is equals to K for this particular case over here. So you can again further simplify that. So for this particular case, so you can write it down the value of your K also. So this is how I can write it down. So the work done, obviously let's say you can just multiply over here gamma minus 1. So let's say this is K1 V1 1 minus gamma minus K2 V2 1 minus gamma. So obviously 1 minus upon gamma. So K1 is P1 V1 raised to, obviously this is P1 V1 gamma and V1 1 minus gamma. Again K2 is nothing but P2 V2 gamma. Again this is V2 raised to 1 minus gamma. So if I simplify this, so what you will get for this particular case, so this is P1, again this is your V1, yeah, and minus P2 V2, yeah. So this is how you can get the value of your work done over here. Now again we know that PV is equals to nRT over here. So for this case also, so the work done is 1 upon gamma minus 1. So nR T1 minus nR T2. So you can take 1 upon gamma minus 1, nR also common, then that is a T1 minus T2. So this is your work done, yeah. So that is the formula for your work done that you will get in case of your adiabatic process, 1 upon gamma minus 1, P1 V1 minus P2 V2, or you can write it down in terms of temperature also, nR gamma minus 1, T1 minus T2.